All right, 3:55. Let's get started. So we're going to start talking about some new stuff in class today, chapter 5. It's a lot of cool stuff. If you have not seen Fourier series before, I think it's pretty nice stuff. So I'm excited to talk about this. So before we get into the thick of things, I want to gently talk about some mathematical preliminaries. So I have 3 questions on the screen. Let's try to think through the 3 questions. So first one, if I have a signal x of t is cosine 2 pi t, and what would we say is the frequency of this signal?
1.
It's 1 hertz, right? Indeed.
Yeah.
So if I change this to sine 2 pi ft, what's the frequency? Oh, so I'm sorry, sine 2 pi t. Also 1 hertz, right? Everybody fine with that? So you may have seen frequency of sinusoids measured in hertz in the past. You have to get used to a slightly different unit. We're going to multiply all the frequencies by 2 pi, which will be what we call as angular frequency. So it's just a transformation where all the frequencies are multiplied by 2 pi, right? And now the units changes. Instead of hertz, the unit will be radians per second. So it's like if you have a sinusoid of frequency 1 hertz, in 1 second it goes through 1 cycle, right? Now imagine if I have a complex exponential whose phase is increasing at the rate of 1 full rotation in 1 second, then I would cover an angle of 2 pi in 1 second, right? So I would say then the frequency is 2 pi radians per second, because in 1 second the angle increased by 2 pi, right? So that's why you multiply by 2 pi. And so it is a little bit unnatural to think of frequency in radians per second. Unfortunately, we're just going to stick to this. It's fairly common to measure frequency in radians per second. It's just a little bit annoying that you have that extra 2 pi to think about, but just something we just have to wrap our head around. Okay? So what would be the angular frequency of the signal in part 1? We would say that the angular frequency is 2 pi times 1, which is 2 pi radians per second. Okay? Usually you use f to denote frequency in hertz. So I would say the frequency is 1 hertz. We're going to use omega to represent frequency when I measure it in radians per second. Okay, so omega is going to be frequency. Okay? All right. Now let's think about the signal x of t is e to the j 2 pi t. So first of all, this is a periodic signal, right? Because e to the j 2 pi t is nothing but cosine 2 pi t plus j times sine 2 pi t. And each one of those terms are periodic. They are periodic with the time period of 1, right? 1 over f, and f was 1 hertz. So e to the j 2 pi t is also periodic with the same time period. So we can talk about the frequency of e to the j 2 pi t, right? And we would say that the frequency of e to the j 2 pi t is 1 hertz or 2 pi radians. That makes sense? So in general, if I have the signal e to the j omega t, so that is a complex signal, right? We will say that it is a complex exponential with a frequency of omega radians per second. Does that make sense? Now notice that omega can be positive or negative. So for example, if I had the signal e to the negative j 4 pi t, then I would say that the frequency is negative 4 pi. So it seems a little counterintuitive at first to think about what is the meaning of a negative frequency. It seems like a frequency of 10 hertz, 60 hertz, 100 hertz. These things seem to make sense. But what's the meaning of negative 100 hertz? All it means is that we are thinking of a signal of the form e to the j omega t. Right? That signal is very well defined, even if omega is negative. Whether omega is positive or negative, it's a very well defined signal. So we can think of complex exponentials whose frequencies are negative. Okay, so this is going to come about in what we are going to do, but let's just keep that in mind. In this example, of course, the frequency is omega, or if we go back to the earlier example, e to the j 2 pi t, the frequency is 2 pi, right? Now, one more thing before we move on. We have already looked at Euler's formula several times in the class. And Euler's formula tells us that we can write cosine 2 pi t as 1/2 e to the j 2 pi t plus 1/2 e to the negative j 2 pi t, right? Now, if you think about this expression on the left-hand side, you have a cosine and the frequency of that is 2 pi. On the right-hand side, you have two complex exponentials, but the frequency of one of them is 2 pi, the frequency of the other one is negative 2 pi. Right? So it tells you it's possible for me to write real signals. Cosine 2 pi t is a real signal. It doesn't take any complex values, right? But I can write it in terms of complex exponentials. But if I were to do that, I might require two terms. One of them may have a positive frequency and one of them may have a negative frequency. It's just a mathematical construct, right? In the end, they add up together and then they just give me cosine 2 pi t. But nevertheless, I can think of positive and negative frequencies together giving me some real signal in the end. That makes sense? Okay? All right. So now we are armed with this. I want to talk about what a Fourier series is. So it's a... So I'll give you a little bit of the history. So Fourier was a mathematician who lived somewhere around 1760 to 1840. So we're talking 250 odd years back. What Fourier was trying to do was he was trying to study how heat is conducted in solid bodies. So imagine you take a plate. I put a heat source in the middle of the plate. Let's say the heat source is something which is changing with time, like a sinusoid. So you're heating and cooling, but like a sinusoid. And what they were trying to study was he wanted to see how, if I picked any point on the plate, what can I say about how the temperature is going to change at that point, right? Because the heat is going to the plate is conducting heat, but it's not going to be exactly the same as what is in the middle. So he was trying to analyze this. What people had done before Fourier was they had realized if the source were actually a sinusoid or cosinusoid, they knew how to compute how the temperature would be distributed on the plate. But they didn't know how to compute the distribution if the source were an arbitrary source. If it's not a sinusoid or a cosinusoid. So imagine I have a heat source which is more like a periodic square wave. So I heat the plate for some time, I cool it for some time. I heat it again, I cool it again. So I do this periodically. So this is not a sinusoid, but nevertheless it's a periodic signal, right? So Fourier was trying to understand how the heat would be distributed on the plate, and he did something remarkable in the process. What he realized was that if you took a square wave, you can actually think of the square wave as the sum of many sinusoids and cosines. And so what he realized was then you could compute how the heat would be distributed for each one of these sinusoids and cosinusoids, which they knew how to do before, and then you can put them all up together. And this is kind of startling. It's even now startling, right? You imagine I'm saying that you take a square wave, and I'm saying that you can write a square wave as the sum of sinusoids and cosines. It just doesn't seem that intuitive that you can actually do this, right? And I'm going to show to you both with the Python program and the math that you can actually write or get a very good approximation to the square wave by just using sinusoids of different frequencies. Okay? So the general result, then Fourier realized, okay, he came up with a general result which says, if you take any periodic signal, so imagine I take a signal, the fundamental time period of my signal is t. So my signal is periodic with a period of t, which means, so I'm going to define something called a fundamental frequency as 1 over t, or angular frequency as 2 pi times 1 over t or 2 pi over t. So we're going to call that as the fundamental frequency of this signal. What Fourier realized or claimed was that you take any periodic signal with a time period of t, you can write it as a linear combinations of sines and cosines, but the frequencies of these sines and cosines are all only integer multiples of that fundamental frequency. So imagine I have something that's periodic with a period of 1 over 100 seconds. Square wave periodic with a period of 1 over 100 seconds. That means the fundamental frequency is 100 hertz, or equivalently 2 pi times 100 radians per second, right? So what he showed was that you can take sine 2 pi times 100, cosine 2 pi times 100t, sine 2 times 2 pi times 100, cosine 2 times 2 pi times 100, 3 times, 4 times, 5 times, and if you all combine them in just the right way, if you take the right proportion of these cosines and sines, when you added them all up, you would get a square wave. Or you take a triangular wave, you just have to change the proportion that you add these signs. So let's get some visual intuition for this. So here are a few periodic signals, right? So periodic signals, they're all periodic with a time period of t. So Fourier's result applies only to periodic signals at this point. We're going to develop something more a little bit later for non-periodic signals. But right now we're thinking of only periodic signals. They're all periodic with a time period of t, right? So the first one is what I would call as a square wave. The second one is a square wave, but it's just shifted up. The third one is a ramp, maybe you can call it as a triangle or a ramp. The fourth one is clearly a triangle. So you have all of these different signals, right? But they're all periodic with the same time period. And this is the picture that I really want you to keep in mind. This is a beautiful picture in my opinion. So I'm going to try to spend some time and explain what's going on here. So imagine I have a square wave. Okay, that's shown in blue. For a minute, imagine that square wave is actually a square wave, right? If you just think about it as a signal in time, then what you really see is that, okay, this is a signal that's changing like this, right? And that's the view if you just see it from this angle. But what Fourier's result tells you is this. If you look at it in the frequency domain, what is really happening is this. What he says is, let's take this signal here, the blue signal. The blue signal is sine omega t, where omega is 2 pi over capital T. I'll write this. So that is this signal. Okay, notice that it has the same time period as that of the square wave. Notice that it goes through one time period exactly where the square wave goes through. So it has the same frequency as that of as the square wave, right? Okay, now pay attention to the green sine wave. So this is also a sinusoid. But the frequency of this sinusoid is twice as large as the frequency of the first one that we took. So you can see it goes through two periods in one time period of the original signal. So that is sine, actually we'll call it omega naught. So this is sine 2 times omega naught t. So that's the green signal. Now the red one is sine 3 times omega naught t, 4 times omega naught t, 5 times omega naught t, so on and so forth. Actually, it turns out, maybe I misspoke a little bit. The green one is actually 3 times. In this example, it turns out that the 2 times is not really required. None of the even, so we call these as harmonics, right? So if I take a sine wave of frequency omega naught, then a sine wave with frequency 2 times omega naught will be called the first harmonic, and then 3 times omega naught, we'll call that as the kth harmonic if the frequency is k times omega naught. So in this example, only the odd values of k are shown. But the beauty is this, and then notice this picture here with the different colors showing the strength of the sine wave, the amplitude of the sine wave. So the blue, green, red, so on and so forth tells you how should I weight, how much should I multiply each one of those sine waves with, and then add them together to get something that looks like a square wave. That makes sense?
Makes sense.
I mean, it's not easy to understand, right? There's no easy way to see it. It's not like I see it either. You have to trust the math to see it or the program to see it. And we will see it in the program that this is indeed true. Yeah?
Be sure in the frequency, that's the amplitude of each of those waves.
Yeah.
Okay, and that's what we're multiplying each wave by.
By, exactly. Exactly. So what it gives you is it gives you a frequency decomposition of the square wave. So what it tells you is that the square wave is actually composed of different frequency components, just like how your voice is composed of different frequency components, right? Like, all our voice is a mixture of many frequency components. If you whistle at a particular frequency, you have only one frequency. Or if you play the piano and you press one key on the piano, you are creating only one frequency. But in general, your voice is composed of many frequency components, right? So we'll get to that, but at this point, I want you to think only about periodic signals, okay? But this picture shows you essentially that at least this periodic signal can be decomposed into its many frequency components, and how much of each frequency component it's there in that signal is given by this plot here. Yeah?
My question was about that. How do you figure out?
We're going to do that. Right now, we don't know how to figure that yet. Okay? So that is called as computing the Fourier series coefficients. We don't know how to compute them yet. We are going to do that in class. Yeah.
Would it be using like a series of waves?
So it is a series of waves, right? What do you mean by would we be using a series of waves?
Oh, no, never mind.
So a few things to keep in mind, but it's true, right? Essentially, it tells you that a periodic signal can be broken down into a sum of many sinusoids. So, I mean, this is one particular example, but a few things are important to note. In general, you may need sines and cosines of the same frequency. It just so happens in this example that you didn't need the cosines, but in general, you may require sine and cosine. Yeah?
The e to the j 2 pi t, would the period be 2 pi and then frequency and angular frequency would it be 2 pi radians per second?
The period would not be 2 pi. The period would be 1 second. Right?
Yeah.
So it's just like sine 2 pi ft.
Yeah.
So f is 1. So if I measure frequency in hertz, it's 1 hertz is the frequency. That means the time period is 1 second. But since I'm measuring frequency in radians per second, it's 2 pi radians per second. Okay? Now, I mean, I know I'm belaboring this, but this image is the most important image to keep in mind. There are a few things to note. First of all, notice how the frequency axis is labeled. Okay, so right now frequency is shown in hertz in this particular picture. So it shows 1 over t, 2 over t, 3 over t, 4 over t, 5 over t, so on and so forth. In general, you can have frequencies. Frequency can change continuously from 0 to anything you want, right? But what Fourier's result tells you is that if your signal is periodic with a fundamental frequency of omega naught or 2 pi over t, the only frequency components that you are going to require are all integer multiples of the fundamental frequency. So you're not going to require anything that lies between 1 over t and 2 over t in hertz, or 2 pi times 1 over t and 2 pi times 2 over t in radians per second. So it's like a discrete set of frequency components, but infinitely many. That's what you mean by a series. So it may be discrete, but I might require infinitely many of them, but I'm never going to require any frequency which is not a harmonic of the fundamental frequency. So if the fundamental frequency is 100 hertz, I'm never going to require 120 hertz to construct that signal. I'm going to require only 100 hertz, 200 hertz, 300 hertz, 400 hertz, so on and so forth. I mean, I may not require some of them, but I will never require something that's not a harmonic of 100 hertz. I mean, none of this is intuitive, okay? None of this at this point is something that you should, oh yes, I don't expect you to know this from before. I'm saying this is what Fourier's result is, and we will show this. Yeah.
So that's coming from the understanding that you have a signal that is only one frequency, right? Because like the human voice is made up of multiple frequencies.
Right.
It obviously has a fundamental. So could you rebuild the signal of the human voice with just its fundamental and just like, so if fundamental of my voice is 200 hertz, I could build it up with 200 and 400 and 600.
So good point. Unfortunately, when you say the fundamental of your voice is 200, how did you say that? What does that mean to you that you say that the fundamental frequency of your voice is 200?
So, thinking how to phrase it. So, trying to think how to phrase it. I know that there is a fundamental of. I wouldn't know how to put it. I just know.
No, there is nothing called. So this is the important thing.
Oh, is there not?
So if a signal is periodic, so if you go press a key on the piano, let's say, I don't know how many of you, if you've seen a piano, I don't know how many of you have played the piano, maybe some of you have played the piano. So you pick a middle C or middle A or whatever, you pick one of the keys on the piano, right? That corresponds to one frequency, right? It's probably like 400 and odd hertz or something like that if you pick the middle one, but regardless, it's one frequency. So we would say that that tone corresponds to one frequency, but what you actually hear because of the acoustics of the piano is you will hear that note, you will also hear some harmonics of the note. This is why one piano sounds different from another piano even if you press exactly the same note, right? But in all these cases, if I press a key on the piano, it produces a sine wave. What you hear is actually a sine wave, right? That is a periodic signal. Yeah. Only then you can talk about something called a fundamental frequency. Because something is periodic, you look at the time period and then you take the inverse of that and you call that as the fundamental frequency. But in your voice, nothing is periodic unless you hum. Let's say you hum at 60 hertz or something like that. Then the fundamental frequency of that signal is 60 hertz. But if like what I'm saying right now, yeah, if you sing a note, then it's okay. Then you can say that there is a fundamental frequency for that. So what you mean by that is, yes, humans are typically able to sing in a certain pitch, right? I'm not very good at singing, but I wouldn't try. Or maybe some of you are very good at singing, and you may sing in a certain pitch. You may sing in a G or a G sharp or something like this. Maybe C if men or women, maybe G or a G sharp. Right, but if you just look at a speech waveform, you don't have anything called a fundamental frequency, but we will get to that later. At this point, I want you to think only about periodic signals. Yeah. So, but if you have a periodic signal, then we have something very clearly defined as the fundamental frequency. Because that's you take the time period, invert it, that's the fundamental frequency in hertz, multiply it by 2 pi, that's the fundamental frequency in radians per second. Okay? But now you can kind of see, notice that all the sinusoids and cosines that we're talking about, their time period is either exactly the same as the signal, or they go through an integer number of cycles within one time period. So when I add them all up, I know for sure that I'm going to get a signal that's periodic with the same time period as the signal that I'm trying to decompose. Right? Now, if I introduced another sinusoid or cosinusoid whose frequency is not an integer multiple of the fundamental frequency, this would not be true. I would be introducing another signal, and that will not go through an integer number of cycles within one time period, right? So I cannot really tell you that it's going to be periodic after I add that. Okay, that's that. So the key result to remember is that you require only the fundamental frequency and its harmonics to be able to construct any periodic signal. You may require the zero frequency too. So zero is also considered as you will call it as the zeroth harmonic. So zero fundamental frequency and integer multiples of the fundamental frequency. Zero frequency means a constant signal, right? DC. DC is a zero frequency signal. How do we define DC? DC is a flat constant signal. So when you add a constant signal, you just push the signal up, right? So in fact, if you look at the difference between the first signal and the second signal here, the difference will be just in the DC component or the zeroth frequency component. Okay, what is beautiful is this. So here I've showed you some pictures. So here is what is going on in these pictures. In all these cases, the first case there is a square wave, in the second case there is the triangle, and then the third case there is another triangle wave. And the different colors in each one of them, the blue color shows you what you would get if I took only the sinusoid or the cosine at fundamental frequency. So imagine I take only the very first term in my frequency decomposition. So if I took only this, that doesn't really look like a square wave, right? And that's why you can see the blue one here doesn't really look like a square wave. But now when I start adding the blue and the green together, I start to get something that looks a little bit more. So imagine what the green thing is doing, right? The green thing has twice the frequency, or 3 times the frequency in this case as the blue. So that's going to make the signal wiggle a little more. And that's exactly what you see here. You see the green one is wiggling a little more than the blue. Now, if I add the red on top of that and I do it just right, now you start to see that I get something that's starting to look more and more like a square wave. So that's basically what that picture is showing. The picture is showing as I add more and more harmonics, I'm going to be able to construct signal that starts to look more and more like a square wave. And the beauty is this. If you change the proportion of these things, you can start to get signals that look like a triangle or look like an exponential. So Fourier's result was that any signal that's periodic, you can basically find some linear combination of the sines and cosines to make it look like that. And that's just a beautiful, it turns out to be a very powerful result in engineering, actually. That everything can be read, every periodic signal can be written in terms of sines and cosines and harmonics of that fundamental frequency. Does that make sense? Yeah. That's the main result. Now, since this result is so important, I also like to think of it as in 2 different ways. I also like to think of this as the equivalent of this as like light passing through prism. So imagine you take white light and you pass it through prism. You see different colors of the light at the output of the prism, right? So what that's telling you is that light is actually composed of different wavelengths. Different wavelengths means different frequencies. What color you get for the light depends on which frequencies you combine together, you get different colors. It's just like that. Your signal is actually composed of sines and cosines of different frequencies. Each frequency you can think of it as a color. What proportion of these you pick to combine will going to give you different colored light to begin with. Okay? All right. Now let's go to the Python notebook and let's see if we can. I'll tell you what's going on there. So maybe we do slightly more math now. So Fourier's result is this. Fourier's result tells you, if you take, by the way, so that's a picture of Fourier. So, well, 250 years back. So,
It's fun. Yeah.
all right. So what we have here is this. We have a signal x of t. It's periodic with a fundamental time period of t. So we're going to call the fundamental frequency as omega naught, which is 2 pi over t. So Fourier's result, and we call this as the trigonometric Fourier series, is that x of t can be written as some constant b0 plus a summation k going from 1 to infinity b sub k times cosine omega naught t. So those are the cosines with frequencies which are omega naught, 2 omega naught, 3 omega naught, so on and so forth, right? Plus, similarly, a sub k times, the second one should be sine k times omega naught t. I'm sorry. This is a typo. That second one should be sine. Well, I can fix it. Why not? All right. So it's a sub k times sine k omega naught t, right? Okay. Now notice that the cosine k omega naught t and the sine k omega naught t can both be written in terms of e to the j k omega naught t and e to the negative j k omega naught t. Right? I can replace the sine and the cosines by just complex exponentials. So when I do that, what I'm going to get is I'm going to get a new series. It's going to look like this. This, I want you to focus on this and make sure we understand the notation here. Let's not worry about what this xk is for now. But what we are going to have, what is, oh shoot, one more mistake here. Yeah. So let's look at this x of t. So it says x of t can be written as summation, but now k going from negative infinity to positive infinity, because I needed the k and the negative k to write my cosine and sine, right? Some constant x of k times e to the j k omega naught t. That makes sense? Now what these xk's are, that's where the secret sauce is. We don't know what they are yet. We're going to learn how to compute those xk's. They clearly depend on the signal x of t to begin with, right? It has to depend on x of t. For different x of t, the x of k's are going to be different. But essentially it tells you when you add them all up, you're going to get x of t. And it turns out there is actually a very, very nice formula for x of k2. We'll show the formula later. For now, you can just see that the x of t, there's a formula that relates x of k to x of t. If I give you x of t, you can plug that into this formula and you can compute your x of t. Okay? Now what I'm going to show in this example is we're going to think about a square wave, but this square wave is slightly different from the square wave that I showed you in the other example. The square wave is slightly shifted from the other square wave. Now notice this square wave is an even function. It's symmetric about the y-axis now. Okay? So what we are going to do is we are going to look at a square wave that's periodic with a time period of 3. And I have shown you only the fundamental, only one period. So notice that the signal goes from negative 1.5 to positive 1.5, right? So it's periodic with a period of 3. But within this period, the signal is non-zero only between negative 1 and 1. So it's a periodic wave, on for 2 seconds, off for 1 second, on for 2 seconds, off for 1 second, so on and so forth. That make sense? Okay. now comes the important part. So what I'm going to do here is this. I want you to look at this, the code here. The first line in the code says n is equal to 1. So what that means, actually maybe we will, you know what, I will run the cell, we'll look, oh, t is not defined. That's not good. Okay. Okay, so I want to show you. So n tells you how many terms I am taking in my Fourier series. Now what do I mean by that? Imagine, so I told you that a Fourier series is written in terms of a summation here, right? So k goes from 1 to infinity. So when I say n equal to 1, what I'm doing is instead of letting my k go from 1 to infinity, I'm going to let it go from only 1 to n. And I first set my n to be equal to 1, which means I'm taking only the first term in my Fourier series. And I'm plotting three things here. The blue curve is just the square wave. It's going to stay constant. The green curve is what you get by taking the first n terms in the Fourier series. So I construct the first n terms in the Fourier series, and then I show you how that is going to change as I increase my n. You take n to be 2, 3, 4, it's going to change, right? The red curve I've showed you on the bottom is the difference between the blue curve and the red curve. Ideally, you want that to go to 0. Okay? Now, you have the curve. You can play around with me too. So what I would like to do is like you to change n. So let's say we change n from 1 to 3. So now you start to get some, let's actually try 2. Why miss 2? So you see, 1 was terrible. I added 2, it kind of got me a little better shape. It's starting to look like a square wave already, right? Now I go to 3, it's slightly better. So you can see because of my increased frequency, I get that little wiggle. Let's go to 5. It's starting to look much better. Go to 10. And you get the point. I go to 20. Starting to look much more like a square wave. So Fourier's result is that if you take more and more terms, your approximation would get better and better. And notice the error here. The error now is very small most of the time. Occasionally it's large, and then it goes to 0 again. Does that make sense? You can play around with it for a while if you want. Try to run it. Yeah.
The 2 on the side, like the red,
Yeah.
is there a way to make that small?
Okay, great question. So this question is what bothered people for a very long time. Okay? So now I'll tell you more history about the Fourier series. So when Fourier came out with this idea, it was not immediately accepted. There were very great mathematicians, including people that you may have heard, Lagrange, Poisson. So they didn't really quite believe Fourier's result at first because they had a very good counter-argument saying that, you're telling me that you're taking sinusoids and cosinusoids, which are all smooth functions. You're telling me that you're adding all these smooth functions and you can get a square wave, which is a discontinuous function. So how can you get a discontinuous function if you end up adding only continuous functions? So something doesn't seem to check out, right? So it was not really accepted at first, and Fourier was also, proof had some issues. It wasn't mathematically correct at first. So there was a lot of reluctance in accepting Fourier's result in full generality, and it took quite a while for people to figure out exactly what's happening. And initially, they thought that, if you computed more and more terms, if you took more and more terms, your approximation would get better and better, and that side lobe will go away. The red thing that bothers you, the two things that bother you, bothered them too. And in 1890, so there was a very famous American physicist and mathematician called Gibbs. I don't know if you have heard of Gibbs in your physics classes. So Gibbs built a mechanical calculator that could compute 90 or 80 or 90 terms of x of k. So you could add them all up together. Then he realized even when you took that many terms, the red thing doesn't go away. Okay? But notice the width of the red. So notice that the width is becoming smaller and smaller as you take more and more terms. Right? So the red signal is the error signal. So it's not that the error signal's height is going to 0, but the width over which the error is high is going to 0 as you take more and more terms. So in the language of signals and systems, what it's telling you is this. If I look at the amplitude of the error, that's not going to 0, but the energy of my error, if I take the energy of this error signal, if I take this signal, I square it and then I integrate it, if the width over which your signal is non-zero is getting smaller and smaller, the energy is becoming closer and closer to 0. So then they realized, okay, what is really happening is that you are approximating one signal by another signal, and the way you are approximating is not what you call as point-wise, which means at every point in time you will not get exactly the same value as the original signal if the signal is discontinuous. So it turns out if the original signal is not discontinuous, then point-wise you will be able to approximate it. But if it is discontinuous, wherever you have discontinuities, you may have this overshoot, but the width of that overshoot will go to 0. For all engineering purposes, that might be good enough. That make sense? Okay, but here is another example. Okay, so now it's not just the square wave, right? So here is an example where let's say the signal is a triangle signal. And so here I take 5 terms of the Fourier series for this, and notice how nice the approximation is just with 5 terms.
We're trying like really large numbers.
Yeah, if you try a really large number, you will break it. The problem is not the computing, actually. So I don't know if when you took your Python class, did you ever play around with the symbolic? So I'm using SymPy for this because the expressions are easy. I would not have normally used that. SymPy has a problem if you take too many terms. So one of the main things that you should realize is this. Whenever you try to write programs to deal with signals, right? If you are interested in a continuous time signal, like what we have here, I have a triangle which is a continuous time signal. So you cannot represent a continuous time signal on a computer. Right? How would you represent a continuous time signal on a computer?
Samples.
So you have to do samples, right? That is the natural way to represent them. So you will have to take many samples and you keep them. If you do that, you will not run into any trouble. But I didn't want to do it at first. I have a separate Python code that does the samples. The reason I didn't want to do it is this code actually computes the. So I want you to look at. This line in the code. Look at what that line is saying. That line is where I compute the coefficients of the Fourier series. That's the line where I say compute 1 over t times the integral of x times e to the negative j omega naught t, integrated from negative t over 2 to positive t over 2. Right? That is how you compute the coefficients. If I had sampled it, I cannot do integrals. I will have to replace this with some kind of summation. That's one more level of complexity I didn't want to deal with in the first class. But you see, that's basically all I did. You take any signal, you can compute this formula, try to reconstruct it, you get your Fourier series. And this is going to form the basis for many things we do, like Fourier transforms will come to human voice and audio in that case. Then it's they are not necessarily periodic, right? Questions?
It's just cool.
It's very, very cool, actually. It is very counterintuitive result, but it turns out to be really useful. Okay. Now we're going to switch back to this. Right. Okay. So when you try to write a signal x of t in terms of sines and cosines, it's called as a trigonometric Fourier series because it includes trigonometric functions, right? But like I just pointed out, you can replace cosine omega naught t by 1/2 e to the j k omega naught t and sine k omega naught t by 1/2 j e to the j k omega naught t minus 1/2 j e to the negative j k omega naught t, right? So when I do that, I will end up with x of t being x of k times e to the j k omega naught t summed over all values of k from negative infinity to positive infinity. But I can compare 5.2 and 5.1, right? After I replace the cosine and the sine with complex exponentials, I can match the terms and I can relate x of k to b and a's. So what I mean by that is, notice if I replace, so maybe I write here. So if I take x of t, I can write it as b0 plus summation 1/2 e to the j k omega naught, bk over 2 plus bk over 2 times e to the negative j k omega naught t plus summation ak over 2j e to the j k omega naught t minus ak over 2j e to the negative j k omega naught t. So now I can combine this bk over 2 and ak over 2j together and think of that as one coefficient. And that is what my xk is. So I would get bk over 2 plus ak over 2j, but ak over 2j is the same as negative j times ak over 2. I use the fact that 1 over j is negative j. And that's how we get xk. And in the same way, I want you to verify x negative k. I will let you do that at home. Okay? So that's, now what you get is what is called as the exponential Fourier series. So this, now we have written x of t in terms of complex exponentials. Now we are going to use that by default. By default, we are going to use the complex exponential Fourier series. And this is what we will call as a Fourier series. The x sub k's or the x of k's are called the Fourier series coefficients. So when I ask you to compute the Fourier series coefficients, I mean compute x of k for a given x of t. Okay? Now, this equation 5.2 is typically called as the synthesis equation. Because what that tells you is that it tells you x of t can be synthesized by taking complex exponentials. It's synthesized by using them, right? So it's called as the synthesis equation. There is an equation that tells you how to compute x of k from x of t, and that will be called the analysis equation because it lets you compute, it lets you analyze x of t to compute the coefficients x of k. Okay? Now, before I go and solve some problems, I want to talk about two things that are really nice. First thing is Parseval's theorem. Okay? Now, if I give you a periodic signal, so for example, that square wave that we looked at, what is the power? How do you compute the power of a periodic signal?
1 over t integral of the magnitude squared.
Oh, very good. So 1 over t. You look at one time period. You compute the energy within that one time period. You divide that by the length of the time period, right? So 1 over t times the integral from negative t over 2 to positive t over 2 or 0 to t, square the signal, integrated, divided by that. So there is some power to this signal, right? But the picture that I showed you tells you that, the signal can actually be written as the sum of sines and cosines. So it must be true that the total power in the signal is somehow distributed in the different frequency components, right? And that's exactly what Parseval's theorem tells you. Parseval's theorem tells you you can compute the power of the signal in another way. You can simply take the Fourier series coefficients, take the magnitude square of them, and add them all up together, and that ought to give you the power in the signal, because that tells you that much amount of power is present in the kth harmonic in your signal. Right? So last time I was teaching this class was when Google had come up with this notebook LM. You are familiar with this thing that creates podcasts based on lectures. So there is Google has a tool, you can upload a notes and it creates a podcast, a 20-minute podcast based on the lecture. So I was curious and I tried that. Last time I was teaching Fourier series at that time, so I created a podcast based on this. It was not bad. And I learned some good analogy to talk about Parseval's theorem. So a good way to think about Parseval's theorem is to imagine x of t is like a smoothie. Okay, so when you make a smoothie, you're going to put many ingredients into a smoothie to create a smoothie, right? You might put some fruits, maybe bananas, strawberries, chocolate chips, nuts, whatever you want to put into them, and then you mix them all up and you create the smoothie. Once you've mixed them all up, you don't see that it's been several things mixed together. So that's like looking at a signal in time. You don't see that it's actually mixed up of separate ingredients. But imagine the calorie content of the smoothie. That's like the power, right? The total calorie content in the smoothie is the sum of the calories that you are getting from the ingredients. Yeah, so the ingredients are the sines and the cosines of different frequencies. So the power in each, the calorie content in each one of them add up to give you the total calorie content of the signal. So, yeah.
I'm just wondering, in that equation you use like 1 over t, but previously we learned that to the power of a constant CT signal is 1 over 2t. In the formula, why is it different?
It's not 1 over 2t.
It's not 1 over 2t?
No, if it had 1 over 2t, it should have an integral from negative t to positive t. So it has to be divided by the length of the interval over which you then. And you typically would not do that for a periodic signal, right? Because a periodic signal is just one period repeated many times. You might as well just compute the energy over one period and divide it by the length of that period.
Would there be any issues with signals, say they have one with omega naught, one with negative omega naught? Is there any canceling out of?
So that is possible, but you cannot cancel out in the following sense. If you take e to the j omega naught t and e to the negative j omega naught t, be very careful between these three things. So the first and the third can add to cancel each other out. The first and second cannot cancel each other out no matter how much you try. You can only cancel maybe the imaginary part. You cannot cancel out the real part ever when you do that, right? Unless you put a negative in front, in which case you will not be able to cancel the imaginary part. So you can never find a linear combination of e to the j omega naught t and e to the negative j omega naught t that goes to 0. Because if you found something, then one would have to be the negative of the other. And they are not. That makes sense? Okay. Now, Another very nice way to think about this is to have a linear algebra interpretation of things. So in linear algebra, I want to refresh two concepts and kind of extend them to signals. And this is actually one of the very powerful and beautiful things in linear algebra. When you took linear algebra, you mostly dealt with vectors, right? If I give you two vectors, what does it mean for one vector to be perpendicular to another vector?
Their inner product.
Their inner product is 0. How do you define the inner product between two vectors?
It's been a second.
Okay, it's usually the dot product where you say that if the two vectors are x and y, it's summation xi times yi, right? You take each component in x, each component in y, you multiply them together, you add them all up. That's the inner product between x and y.
It doesn't have to be though, right?
Well, unless you put some weighting on it. It could be a weighted inner product, but I don't know whether you actually covered that in 3.0. I would be a little bit surprised if you covered weighted inner products, but what else do you have in mind? It's true that it does not have to be this, but this is the most common thing that you would have seen in your linear algebra class.
I'm trying to think because standardly that's 2, but you could have, say, norm 1, which would just be the max of it. You would have.
But those are all norms. They are not inner products.
But the norm's defined as the square root of the inner product, is it?
Not always. Okay, so we're getting a little bit of linear algebra. So the inner product between two vectors is typically called the dot product. If I take the inner product of x with itself, then I would get summation xi squared, right? We would call that as the square of the two norm. You can define other norms. For example, a norm is like a measure for how big a vector is, roughly, right? The square of the two norm is just your usual length of the vector squared. Because if I take summation xi squared, I get the length of the vector squared. Now I can define another norm where I say if I take a vector, I can look at the largest value of the elements in that vector, and I can think of that as how big that vector is. That's called the infinity norm. But that norm is not induced by inner product. You cannot find an inner product such that x times x inner product with x will give you that norm. So not all norms are induced by inner products in linear algebra. But this is the most common one you see, right? This is the dot product between two vectors. And you say that x and y are orthogonal if this dot product is equal to 0. Like for example, here are two vectors. If I take the dot product between them, the dot product would be 0, right? 1 times 1 plus 1 times minus 1. And normally, do you remember what a basis is in linear algebra? So a basis is just a set of vectors such that you can write any vector in that space as a linear combination of the basis vectors, right? So in 2 dimensions, you can say I either take the vector, let's say 1, 0, 0, 1, and then I say that any vector in 2 dimensions can be written as a linear combination of these two vectors. You agree? But I can also rotate these two vectors. Now imagine I change my axis such that my axis looks like this. So let's say this is 1 over square root of 2, 1 over square root of 2, negative 1 over square root of 2, 1 over square root of 2. Now these two vectors are also orthogonal to each other, and they also form a basis for the 2-dimensional space, right? Any vector in 2 dimensions, I can write it as a linear combination of these two vectors. Do you agree? So now we found 2 different bases for exactly the same space. The space is the space of all 2-dimensional vectors, and I found 2 different bases, both of them having orthogonal vectors. You agree? So this is exactly what is happening with signals and Fourier series. So what Fourier series is saying is this. Imagine I take the set, instead of thinking of vectors, think of signals. Think of each signal as one basis vector. So imagine I take the signals which are all e to the j omega naught t. e to the j 2 omega naught t, e to the j 3 omega naught t, e to the negative j omega naught t, so on and so forth. Think of all of these as vectors. Think of all of these as basis vectors, right? What Fourier's results tells you is that this forms a basis for periodic signals, which means if I give you a periodic signal, you will be able to write it as a linear combination of these signals. So that's what it means for something to be a basis. That make sense? And just like how these vectors were orthogonal to each other, turns out all these signals are orthogonal to each other. So what do we mean by orthogonal to each other? Now what does it mean? So we know in vectors what it means for two vectors to be orthogonal to each other. That means that their dot product is 0. So we can define something which looks very much like a dot product but with signals instead of vectors. So imagine I define the dot product between two signals. If they are real, I define it as the integral of x of t times y of t. See, it looks very much like the sum of xi times yi. X of t times y of t, instead of sum I have integral. So we call this as the inner product between x of t and y of t. If this inner product is 0, we say that these signals are orthogonal to each other. And geometrically they look exactly like vectors. If you want to, I mean it's kind of hard to picture it, but they play the same role. Like they are basis vectors of some space and they are orthogonal to each other. That makes sense? I know this is a little bit abstract, but we won't push it much more in this class. But I think if you like linear algebra, this would, you would enjoy this. But I want to go back to Parseval's theorem and then make sure that we have a good interpretation for x of k. So let's look at 5.9 one more time. 5.9 tells you the power in the signal x, I can either compute it in time or I can take the square of the magnitude of each Fourier series coefficient and add them up. It gives me the same answer. So that tells you that we can interpret the magnitude of x of k squared as the amount of power that is present in the kth harmonic. Right? So it tells you that your total power is distributed in the different harmonics. How much of it is present in the kth harmonic? Well, that's magnitude of x of k squared. It's like you made a smoothie with different proportions of bananas and strawberries. Like in this smoothie, how much of the calorie comes from bananas, right? And you would look at how many bananas you put and you compute that based on that. That's exactly what's happening here. And just in terms of notation, so the term corresponding to k equal to 0 is of course the DC term, and all right. Now, so what we have now is a signal x of t, periodic signal in time. It's a continuous time signal, right? X of t is a continuous time signal. You agree? But when I computed the Fourier series coefficients, the frequencies that are all present, they are either 0, fundamental frequency, 2 times the fundamental frequency, 3 times the fundamental frequency, -1 times the fundamental frequency, -2 times. So they're all integer multiples of a fundamental frequency, right? So if I now imagine this as a signal with frequency being the independent variable. Imagine we talked about discrete time signals in the past in class, right? Now if you think about the Fourier series coefficients, it's a discrete frequency signal because the only frequencies that are present are 0, omega naught, negative omega naught, 2 omega naught, negative 2 omega naught, 3 omega naught, negative 3 omega naught, so on and so forth. I can drop the omega naught and I can just pretend like this is defined on integer values of frequencies. So when we write the Fourier series coefficients, we can write it like how you would write a discrete time signal in terms of delta functions, I can use delta functions with k as the independent variable to write the Fourier series coefficient, right? So we'll take a quick example. Let's look at the signal x of t is cosine omega naught t. So clearly I can write cosine omega naught t as 1/2 e to the j omega naught t plus 1/2 e to the negative j omega naught t. Now I already have my x of t written in terms of complex exponentials, right? If I'm looking for a Fourier series representation, what this means is I want to be able to write my x of t as linear combinations of complex exponentials. If I'm able to do that, whatever the coefficients are in this linear combination, they are my Fourier series coefficients. In this case, there are two non-zero coefficients, the term corresponding to k equal to 1 and the term corresponding to k equal to -1, right? Because I have this term corresponds to k equal to 1, this term corresponds to k equal to -1. Because it's sort of the form e to the j k omega naught t. Is that clear? So keep in mind that we want to write our x of t as x of k times e to the j k omega naught t. So if you match these two together, you notice that only two of those terms are non-zero, right? Because you have only two terms, half e to the j omega naught t and half e to the negative j omega naught t. The first term corresponds to k equal to 1. The second term corresponds to k equal to -1. A nice way to write that is to write x of k as 1/2 times delta of k minus 1 plus 1/2 delta of k plus 1. That make sense? So we will write the Fourier series coefficients in terms of delta functions in k. So it's like a discrete frequency signal. Very good. I think what remains is to compute this x of. So it turns out that x of k can be written in terms of x of t. I won't derive this equation, but I want you to focus on the equation and we make sure that we understand how to compute this. So it turns out if I give you a x of t and I ask you to compute x of k, you can take the integral over one time period. Integral over t means either you integrate from -t over 2 to +t over 2 or 0 to t. You choose whatever you want to integrate. It doesn't really matter. 1 over t times integral x of t times e to the j k omega naught t dt. And we will solve some examples. I will get clearer when we do this. But that is an equation that will give you x of k for a given x of t. So notice on the right hand side I have an integral. The integral is with respect to time. So when I compute that integral, in the end t will vanish because I will plug in the limits of the integral. T will go away. The only variable I will be left with are k and omega naught. Of course, omega naught is a constant because it depends on the, I tell you a signal is periodic with a certain time period, then omega naught is fixed. But it tells you now, it gives you an expression that's valid for all k. Does that make sense?
Out of curiosity, why is there a negative sign for the e to the negative jk omega?
Yeah, you have to see the derivation for that. Okay, it's actually a really good question. Now, I wasn't really very careful with something. The correct inner product between two complex signals is actually x of t times y conjugate of t dt. And that's where that negative comes from, because you have to conjugate one of them. I was a little cavalier. I was just looking at real signals at that time. But I have a proof in the notes. If you follow the proof, you will see where it comes from. I won't go into the proof. I don't have time. I have only 6 minutes. So what I want to do in the last 6 minutes is, so in the next class we're going to solve many problems for this. But before I go that, I want to go all the way back to chapter 2. In chapter 2, we defined many signals. If you remember, we defined unit step, we defined delta function, we might have defined a few other signals. But there is one signal I didn't talk about then, now which I want to talk about now. This is called the sync signal or the sync function. It's not the sign, but it's the sync, S-I-N-C. Okay? The definition for the sync function is that sync of t is defined to be sine pi t divided by pi t. Okay? I give you a t, sine pi t divided by pi t. Well, the problem with sine pi t over pi t is if t is 0, you get 0 over 0. Right? So at t equal to 0, we're going to define it to be 1. So we avoid having to deal with 0 over 0. But it also makes the signal nice and continuous, because if you take the limit as t goes to 0, this function is indeed 1. So when I plot the signal, you get something very nice and smooth, like this. Let's think about the sine signal, right? Sine pi t divided by pi t. Now, if the denominator were not there, if this pi t were not there, then it would just be a sinusoid. What's the effect of dividing by pi t? Well, the effect of dividing by pi t is as t becomes large, your denominator becomes large, so your sync is the sine is going to kind of taper out. And that's what's happening in the picture, right? However, notice that so let's think about what will be the values of t for which the sync crosses zeros. What are all values of t for which sine pi t over pi t is 0?
Integer multiples, or just integers actually?
Just integers, right? Because yes, I want sine pi t to be equal to 0. So when t is 0, sine pi t is clearly 0. When t is 1, I get sine pi. Sine pi is 0. T is 2, sine 2 pi is 0. So all integer values of t are going to give me a sync to be 0. So keep that in mind. Sync t crosses zeros at every integer multiple. Okay? Now this sync function is going to show up many times over the next few weeks. Right. So let's do two examples just to make sure we get comfortable with these sync functions. Sometimes you might see things that are not explicitly written as sync functions, but they can be actually written in terms of sync functions. So for example, remember my definition for the sync function is that it's sine pi t over pi t. But if I have the signal sine a times t divided by a times t for some value of a, maybe a is 3 or something like that, how can I write it in terms of sync functions? Well, one thing you can do is you can write sine at divided by at, you can write it as sine pi times at over pi divided by pi times at over pi. I just multiplied and divided by a pi, right? Now if I treat this as my t, then this is nothing but sync at over pi. That makes sense? And if you can do the reverse, it's easier to see. Sync at over pi by definition should be sine pi times at over pi divided by pi times at over pi. It should give me back sine at over t over at. The last thing in the 1 minute that I have left, we'll look at sine at over bt. Okay. The trick we can play here, we do something very similar. So what I want to Oh, I guess it doesn't want to work in the last minute. My pen doesn't want to work. It's tired. You know what that means? Homework. Since we have only a few people in class, we can quickly do it on the board.